Hello, and welcome back to the course on University Physics 3. This is now the second and last lesson for Chapter 10. So before we proceed, let us review the previous lessons. So we have discussed about self-inductance or inductance, and it's given by this equation. So it's dependent on the number of turns, the flux, and the current. So the self-induced EMF is also proportional to the inductance and to the change in current with respect to time. So in this lesson, we will try to analyze inductors in circuits in different scenarios. So whether it is it's connected to a resistor or a capacitor or both. So let's first start by connecting our inductor with inductance L to a resistor with resistance R. And we call that connection an RL circuit. So this is a resistor and a conductor in series. So here is your resistor and here is your inductor. So at first, there's a switch here. When you close the switch S1, you are actually basically charging the inductor in that case. And if you open S1, the switch S1 and close S2, then the conductor in this case is discharging. It's actually giving energy to the resistor. So in the first case, when the switch S1 is closed and the switch S2 is open, there will be a current growth. So the current inside the current in the circuit will actually grow. So the growth is actually exponential. So the current is actually the EMF of your source over the resistance times 1 minus this exponential term here. So it's a current growth. It's an exponential growth. So the time constant corresponding to tau, which is just L over R. So if you divide the inductance by the resistance, it has a unit of time, so seconds, and that's actually the time when the current is now 67% or 2/3 of its final value. So that is the time constant. So if we use Kirchhoff's rules here, Kirchhoff's loop rule here, the summation of voltages will be like this. So EMF minus IR minus L di dt. So in that case, the inductor is actually charging. So in this case, the inductor is now discharging. It's actually giving energy to the resistor. So there will be a current decay. There will be a decrease in current. So we now close S2 and open S1. So the current decay is given by this expression. And of course, the time constant, which is L over R, is the time when the current is already 2/3 of its initial value, which is I naught. So I naught is the initial value. And using Kirchhoff's rule, since there are only two circuit elements, this is the Kirchhoff's summation of voltages. Okay, so let's have an example. So a sensitive electronic device of resistance R equal to 175 ohms is to be connected to a source of EMF by a switch. So the device is designed to operate with a 36 milliampere current, but to avoid damage to the device, the current can rise to no more than 4.9 milliamperes in the first 58 microseconds. So an inductor is therefore connected in series with the device. The switch in question is S1. So we don't bother with the lower part of the circuit for this problem, only the upper part. So as you can see from the problem, the purpose of the inductor is to regulate the current. So the inductor is connected so that the current will not rise to more than 4.9 milliamperes in the first 58 microseconds. So the first question is, what is the required source of EMF? Then what is the required inductance? And what is the time constant? Okay. So for letter A, for the required source of EMF. So it's just I times R. So the 36 milliampere current here is assumed to be the final current, the final value of the current. So you will have 36 milliamperes, which is milli means times 10 to the negative 3 milliamperes. Resistance is 175 ohms, so the final unit of that is volts. And you will get 6.3 volts. So this should be the EMF, 6.3 volts. Now what letter B? What is the required inductance? So we know this is the expression for the instantaneous current, E over R, for current growth. No? It's 1 minus e to the negative R over L times T. Okay, we know the value of the current. The maximum current should be 4.9 milliamperes at a time of 58 microseconds. We know I, it's 4.9 milliamperes. We know the time, it's 58 microseconds. We know the resistance. We know the EMF. The only unknown here is L. So solve for L. So I'm no longer gonna, so that I'm solving for L, and I get L is equal to negative R times T over Ln of 1 minus I over capital I. The current, the 4.9 milliampere current over the final current, which is 36 milliamperes. And you will get, substituting all of that, you will get 69 millihenries. That is the required inductance. So what is the time constant? So for letter C, the time constant, the time we're in, the current is 2/3 of its final value, meaning the time where 2/3 of 36 milliamperes is 24 milliamperes. The time when the current is 24 milliamperes is L over R. So you know the inductance, 69 times 10 to the negative 3 henries. You know the resistance, 175 ohms. You divide that, and you will get 390 microseconds. So these are the summary of our results. So the required EMF is 6.3 volts. The required inductance is 69 millihenries. And the time constant, the time when the current is 2/3 of this final value, 2/3 of 36, which is 24 milliamperes, is 390 microseconds. So let's now go to the second circuit connection. This is an inductor capacitor connection. So in an inductor capacitor circuit or LC circuit, you will expect to have electrical oscillations because a capacitor stores electric potential energy and an inductor stores magnetic potential energy. So there will be oscillations from electric to magnetic potential energies and vice versa. So they're basically just trying to charge each other. So the capacitor charges the inductor, and then the inductor charges the capacitor, and vice versa. There will be electrical oscillations. So the angular frequency of these oscillations, the transformation from electric to magnetic potential energies back and forth, is given by this value, or this expression, square root of 1 over the inductance times the capacitance. So that one. And the instantaneous current in this case is actually negative omega q sine omega t plus p. So it's actually sinusoidal. The current is sinusoidal and it is actually negative. So since the energy is oscillating, transforming back and forth to electric and magnetic potential energies, then you expect the current to also be oscillating in the opposite direction, hence the negative sign here. Okay. So conservation of energy in an LC circuit goes like this. So the energy, the instantaneous energy in the inductor, the small i's and the small q corresponds to instantaneous values at that moment or instant. The instantaneous energy of the inductor plus the instantaneous energy of the capacitor is equal to the total energy when the capacitor is full charge, or this is also equal to the total energy when the inductor is full charge. It's also equal to 1/2 Li squared. So for now, we'll just consider the capacitor. So the analogy of this is similar to a mass spring system. So if you have a mass connected to a spring, this is your spring and you have a mass M connected to a spring, this will actually oscillate in the same manner. So when the spring stretches out to its maximum stretch, the energy is potential, and then it goes back to kinetic, and then potential, and then kinetic, potential, kinetic. So that's the analogy of the angular frequency of oscillations in an inductor capacitor circuit. So basically, in this case, it's magnetic potential energy to electric potential energy and vice versa. Okay, so let's have an example. Sorry. So a 300 volts power supply is used to charge a 25 microfarad capacitor. After the capacitor is fully charged, it is disconnected from the power supply and connected across a 10 millihenry inductor. So our setup looks something like this. You have a 300 volts power supply, that's the EMF, 300 volts, and it's charging a capacitor. So there's a switch here, and then later you connect it to an inductor. So this switch, after the capacitor's capacitance C is fully charged, you flip this switch here so that it will be disconnected from the supply, and it will now be charging the inductor, and there will be oscillations there. Okay, so you are the capacitor is connected to a 10 millihenry inductor. So this is 10 millihenry. The resistance in the circuit is negligible, so there's no resistance. So find the frequency and period of oscillation of the circuit. Okay. So when we are asked of the frequency, it's F, and it's related to the angular frequency omega by 2 pi times F. So the angular frequency is square root of 1 over L times C. Therefore, F is just equal to 1 over 2 pi square root of 1 over LC. So we are given the inductance 10 millihenry. We are also given the capacitance is 25 microfarad. Just convert that into the standard unit. So 25, this is 25 times 10 to the negative 6. This is 10 times 10 to the negative 3. And you will get a value of 320 hertz. That is the frequency. Take note that the problem requires us to solve the frequency. And what is the period? The period is just 1 over the frequency. So 1 over this, you will get 3.1 times 10 to the negative 3 seconds, or 3.1 milliseconds. So that is the period. Okay. Second problem. Find the capacitor charge and the circuit current 1.2 milliseconds. So I'm just going to erase this one. 1.2 milliseconds after the inductor and capacitor are connected. Okay. So from this figure, the capacitance is actually just the final charge, the full charge of the capacitor over the EMF, or the voltage. So therefore, the full charge of the capacitor, Q, capital Q, is just the capacitance times the EMF. So we will use this value later. So the current in an LC circuit is actually given by negative omega Q sine omega t plus P, omega t plus P. So this one. So we will assume that the initial phase angle is 0, and this is actually equal to the negative dq dt. So that's the definition of current, right? Current is change in charge, dq dt. So it's negative because the charge is actually decreasing. So after you switch this to here, then the capacitor charge starts from an initial value of q and it's decreasing. So it's negative dq dt. And the capital Q is the full charge. This is C capacitance times the EMF. So we have something like this. The negative sign will cancel each other out. You have omega. This is capacitance times EMF. This is just sine omega t. And you have dq. Now we'll cross multiply dt. So there will be a dt here. It's dq. So we have a differential equation now. So we need to solve for the charge. We are asked actually for the capacitor charge, Q, at time is equal to 1.2 millisecond. So how do you solve for Q? Integrate this one, and you will get Q is equal to negative C and the EMF cosine omega t. So this is your, I will leave the integration to you. So you will get this result. So at time is equal to 1.2 milliseconds, the charge is negative 5.5 times 10 to the negative 3 coulomb. So at time is equal to 1.2 milliseconds, that is the capacitor charge. So what is the circuit current? The circuit current is just this one, so you use this value. So at the current, you will get current of negative 10 amperes. So this is the formula for the circuit. So Q is just C times that one. So that is the capacitor charge, and the circuit current 1.2 milliseconds after the inductor and capacitor are connected. And here are the summary of our result. So for the last topic of this lesson, we go now to the complete package: a resistor, a conductor, a capacitor in series. So this is what we call an LRC circuit. So you have a capacitor, you have a resistor, and you have an inductor. So initially, the switch is in this direction or in this orientation. So only the capacitor is connected to the EMF. So the capacitor is actually charging. So once the capacitor is fully charged, you switch the switch from this point to point A, and then the capacitor will now give energy to the resistor and to the inductor. And there will also be oscillations in this case because when all of the energy of the capacitor is, or some of the energy of the capacitor is in the inductor, then the inductor will now be charging the capacitor again, and the current will be oscillating. So if the resistance is just small enough, the oscillation will look like this. So it's what we call an underdamped oscillation. It's oscillating with a certain frequency, but the intensity or the amplitude of oscillation is actually decreasing. So we call this underdamped oscillations. And the angular frequency is square root of 1 over LC minus this term here. So you will notice that if there's no resistance, this just reduces to the LC circuit, angular frequency of the LC circuit, the undamped. There's no damping involved here. Damping means the decrease in amplitude. So there's no damping in that case. But if you have a resistance, then there will be damping. So that one. Now, if the resistance is very large or large enough, then you will have a critically damped oscillation. And if you have a very large resistance, then you will have an overdamped oscillation. So basically, there's no oscillation in that case. Okay. For our last example, in the LRC circuit, if the inductance is 10 millihenry, the capacitance is 25 microfarad, what resistance is required to give the LRC series circuit a frequency of oscillation that is 1/2 the undamped frequency. Okay, this is a very interesting problem. So the angular frequency for undamped oscillation in an LRC circuit is given by this one. 1/LC minus R squared over 4L squared. So according to the problem, what resistance is required to give for this angular frequency of oscillation to be equal to 1/2 of the undamped. The undamped frequency of oscillation is square root of 1/LC. That one. So in this equation, L and C are given. The only unknown is R. Solve for R, and you will get R is equal to square root of 3L over C. And you will get a value of 34.6 ohms. So that is the frequency required so that the frequency of oscillation of this LRC circuit is 1/2 of that of an LC circuit, the undamped oscillation. Okay. So that's the end of this lesson and basically the end of the chapter. So the last chapter of this course will talk about alternating current. What are some of the properties of alternating current and what are their applications? It's still all about electromagnetic induction. So I will see you again in the next chapter.